describes the Argus experiment, a nuclear test conducted within the time period of Operation Hardtack, but in a different location and by a separate organization, the Advanced Research Projects Agency of the Department of Defense, assigned to the Armed Forces Special Weapons Project responsibility for conducting the Argus test and for coordinating the activities of all participating agencies. This motion picture can serve a dual purpose. It will be my preliminary report to the Advanced Research Projects Agency, and it can serve as an orientation for those previously unfamiliar with Argus. For this reason, the report includes a discussion of the background as well as the execution and findings of the project. More detailed written reports are, of course, being prepared. To administer Argus, a special weapons test project was organized within AFSWAP to function under command of Rear Admiral Lloyd M. Mustin. Admiral Mustin also assumed personal command of Task Force 88, created to carry out the seaborne phase of the operation. The major participating agencies were the Army Ballistic Missile Agency, Air Force Special Weapons Center, Air Force Cambridge Research Center, and Sandia Corporation. Navy participation included technical aspects carried out under the Office of Naval Research and the furnishing of Task Force 88 for operations at sea. To explain the nature of Argus and its background, I will call on Captain William Wallace, USN, who was Senior Technical Staff Officer of the task force, as well as Chief of the Analysis Division of AFSWAP.
To begin with a simple statement, the objective of the Argus experiment was to take a close look at the phenomena associated with the trapping in the Earth's magnetic field of relativistic electrons produced by nuclear detonations at very high altitudes. It was necessary to learn the governing parameters of these phenomena so we could make reliable estimates of their military importance. There seemed to be a good possibility that they were very important, and for that reason, there was a pressure on this entire operation to secure quick results. In our school days, we learned that the magnetic field of a common bar magnet can be represented by a set of lines. Fields of this type are commonly called dipole fields. Of course, such fields do not lie in a two-dimensional paper-flat plane like this. In a top or bottom view of the magnet, the field lines would be shown as a sort of fringe sticking out all around it. Actually, this concept of lines of force with spaces between them is misleading. There are no separated lines of force around a magnet, but only a zone or field of force. And the lines are a handy convention to indicate the relative strength and direction in which the field exerts the force in different areas. A close spacing of the lines is used to indicate areas where the field is strong. The Earth itself is a magnet. It acts as a dipole surrounded by a field of magnetic force. The directions in which the force acts are again illustrated by lines. The field lines at high latitudes were not involved in the Argus experiment, so for simplicity, we'll drop them out of the picture. Looking at this cross-section view, we see that the magnetic field extends a great distance from the Earth, so we need a number of layers of lines to show the strength and direction of the field at different altitudes. Remember that this is a cross-sectional view. Any one of these field lines can be thought of as lying in a shell, made up of lines of that particular size and extending to the same altitude all around the Earth. Perhaps the easiest way to visualize this is to picture each shell as roughly like a giant automobile tire around the world. The tire beads, which are the north and south edges of the shell, will describe rings on the Earth's surface corresponding to north and south geomagnetic latitude lines around the Earth. For the concept of many layers of shells, we picture concentric layers of tires, each nested inside of the next bigger tire. The magnetic surfaces and field lines illustrated by these tires are the foundations of our project. Accepted theory tells us that if a charged particle like an electron moves in a magnetic field, it may, under certain circumstances, be deflected into a helical or spiral path, winding around the imaginary magnetic field lines. As this previous chart showed, the Earth's magnetic field lines converge to a denser pattern at both their north and south ends. If a particle trapped in the Earth's field spirals into such an area where the field lines converge, the spiral gets progressively flatter and finally reverses, and the particle goes right on back the way it came, spiraling around the same lines, having lost very little energy from the change at the mirror point. Now, if we think of this effect in relation to some given magnetic line of force in the Earth's field, we see that such a particle might be trapped and mirrored back and forth for a considerable period, if the reversal or mirror point is located high enough, substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle and soon be lost by collision with air molecules. A mechanism similar to this is accepted as one of the causes of auroras. Streams of charged particles ejected from the sun reach the Earth and are trapped in some set of the Earth's field lines. Those particles with low mirror points hit and excite the atmosphere at each end, or conjugate point, causing the auroral glow. Aurora borealis in the north, and simultaneously an aurora australis in the south. Now, there is one other important effect that operates here. If we look northward, directly along a group of magnetic field lines, we could picture their imaginary ends as an equal number of imaginary points. From here, we might expect to see any spiraling electron describing neat circles if it travels in a uniform field. However, the magnetic forces around the Earth are not uniform. They are stronger at lower altitudes, which we show by a denser concentration of lines, or from this angle, dots. In this environment, the path of the spiraling electron is not perfectly circular. It tends to turn in a tighter arc in the more intense field at the bottom of each loop than at the top. As a consequence, the trapped electron's helical path has a substantial component of migration to the east as it shuttles back and forth, north and south. If it were a positively charged particle, it would migrate to the west. But we are only interested in electrons at the moment, high-energy electrons, with speeds so near the velocity of light that we must apply Einstein's laws of relativity in dealing with them, which is why we refer to them as relativistic electrons. Their energies are in the neighborhood of 1 to 6 million electron volts. Here, again, is a representation of a layer of the magnetic field surrounding the Earth. If a quantity of relativistic electrons is properly injected into this field at a given point, some percentage of them would not only be trapped into shuttling back and forth along the field lines, but would also migrate eastward, spreading a shell of electrons entirely around the Earth. An approximation of this effect can be shown with a device developed by the Naval Research Laboratory and called a sturmatron, as a tribute to the Norwegian physicist Carl Sturmer. Here, a beam of electrons is directed at a small spherical dipole simulating the Earth in an evacuated chamber. The magnetic field of the sphere traps the particles into a path outlining the magnetic field in the same general contours we used in our drawings. Observe particularly the two fluorescing bands traced around the sphere like latitude lines, where the north and south edges of the electron shell contact the surface. If we look at the effect from the direction of one of the poles, the field is seen as a symmetrical circular fringe, as would be expected. The background up to this point explains the nature of what has become known as the Argus effect. The trapping of injected electrons into a shell spread around the Earth, and the subsequent effects caused by these electrons. As I said earlier, the elements of this theory had been rather generally accepted long before this operation. The aspects which were new and which interested us were the military implications. These aspects were explored in a theoretical work by Mr. Nicholas Christophilus, a physicist with the University of California Radiation Laboratory. It was pointed out that the explosion of nuclear weapons at a proper height above the Earth could inject into the magnetic field a large quantity of relativistic electrons derived from beta decay of the fission products. Christophilus predicted that the trapped electrons would, as a consequence of their spiraling flight, emit a form of synchrotron radiation. A simpler name for this is radio noise, with a very wide band or white noise spread of frequencies. Now suppose we have an anti-ICBM radar looking north here to watch for any enemy missiles coming over from that direction. Next, suppose that an enemy, just before launching his missiles, detonates enough high-yield, high-altitude fission weapons to spread a shell of noisy electrons all around the world. Electrons emitting radio noise in the frequencies our radar uses. The shell would amount to a screen that could severely limit the range at which our ballistic missile early warning system could see oncoming missiles, or could conceivably blind the system entirely. It appeared that if a sufficiently dense relativistic electron shell were established, any ICBM penetrating the shell would be surface heated to such a degree as to make it a bright target for heat-seeking anti-missiles, which would allow detection and defense even if our radar performance were degraded. Beyond this possibility, a layer of electrons could conceivably be established sufficiently dense to overheat and actually destroy by burning any penetrating ICBM. It did appear that the fission yield required for any such effect might be prohibitively high from several points of view, on the order of many thousands of megatons. However, this was one more question that could not be given any definitive answer with the information at hand. For a valid survey of the military implications, we had to plug some of the thin spots in our theoretical structure with actual experiment. We had to know a number of things. First, did the Argus effect, the trapping and shuttling and electromagnetic noise generation of the high-speed electrons, actually occur as we believed? If it did, what was the trapping efficiency of the effect at heights of interest? In other words, if a nuclear weapon were exploded at altitude, how many of the available relativistic electrons from a given fission yield could we expect to be trapped into orbits that would produce a stable electron shell? Then, how stable would the shell be? What would be the effective lifetimes of the orbiting electrons? In order to answer these and other equally relevant questions, the Advanced Research Projects Agency requested Chief ASFOP to get Argus moving as quickly as possible. The operational concept was simple, at least in statement. A rocket with a small nuclear warhead was to be taken to the South Atlantic and fired to burst at a height of roughly 400 miles. Observers and instruments were to look for Argus effect data at the firing point and at the calculated mirror point, or conjugate point, at the equivalent geomagnetic latitude in the northern part of the Atlantic. Prior to the burst, several instrumented satellites were to be placed in orbit around the Earth. The closer to a polar orbit, the better for our purposes. When and if the high nuclear burst established an electron shell, the satellites would detect the increased electron density every time they passed through the shell, which would be 4 times on each trip around the Earth. Telemetering of the satellite signals to ground stations would then give the information we needed. Still another program was to utilize instrumented high-altitude sounding rockets to telemeter data obtained by passing through the shell, either from below or from the outside. Development of most of the subdivisions of the job took place concurrently because of the pressure to hurry things up. As Admiral Parker stated earlier, Task Force 88 was created to handle the naval phase. A test project headquarters, designated Task Group 88.6, was established in the Pentagon. The vehicle selected to deliver the warhead was the X-17A, a three-stage solid propellant rocket which had already been thoroughly tested and proved as a vehicle for Air Force and then later Polaris nose cone re-entry tests. The launch ship was the USS Norton Sound, based at Port Hueneme, California. She is a seaplane tender converted to a missile ship and required little modification for X-17A launchings. Before leaving for the South Atlantic, Norton Sound took 4 X-17As out for test firings in July off the California coast. This was both to work any bugs out of the equipment and system and to provide experience for the launch and tracking crews. The rocket's third stages were equipped with beacon transponders for radar tracking purposes. Their dummy warheads contained instrumentation to telemeter performance of the arming and firing system. Shot number 1 went off well. Stabilized by the small spin rockets belted around the first stage, the rocket reached altitude successfully. Note that the spin rockets fall away from the main rocket body as soon as the rotation is established. Rocket number 2 launched satisfactorily, but broke up in flight with wild veering. Rocket number 3 also broke up in flight. It was concluded that the induced spin rate was coinciding with the resonant frequency of the vehicle in the new configuration used for this particular project. To eliminate this source of trouble, the spin rockets were omitted from rocket number 4, with a hope that the consequent increase in dispersion would be acceptable. The cure worked, and rocket 4 flew satisfactorily, reaching a height in excess of 300 nautical miles. Incidentally, for convenience and consistency, we will use nautical miles as our dimensional unit throughout this report. After these trials, Norton Sound returned to Port Hueneme. 3 operational X-17A rockets, the nuclear warheads, and other general supplies were loaded aboard. Then the ship departed for the South Atlantic launch rendezvous, which was designated as Point Lima. The route selected for maximum security cover was down the west side of South America and around Cape Horn, then east to Point Lima. August is midwinter and cold in the South Atlantic. No routine activities such as whaling are likely to bring ships into the area at this season. This remoteness contributed to the security of the operation. The remaining ships of Task Force 88, assembled at and departing from the East Coast, were 2 destroyers, 2 destroyer escorts, 2 oilers, and the aircraft carrier Tarawa, with crews totaling some 4,000 men. Tarawa was the flagship of Admiral Mustin, who embarked at Quonset Point. These ships departed for the South Atlantic in early August, with no stops scheduled en route. As is normally the case when circumstances permit, Davy Jones, King Neptune, and his court came aboard as the task force crossed the equator. A number of minor sentimental touches were devised to bring the dignity of the occasion forcefully home to the new boys, the pollywogs, making the crossing for the first time. The main feature cooked up for the passport ceremonies involved a mixed grill of military and scientific personnel being basted to a turn, an event which tended to stay in the backs of their minds for some days thereafter. Proceeding southward, the timing of the ship movement was such as to bring the East Coast contingent to Point Lima at the same approximate time that Norton Sound arrived there. Selection of this particular locality out of the vast area at hand was dictated by a sort of reverse process. To begin with, we are accustomed to Mercator projection maps with straight latitude and longitude lines at neat right angles to each other, and based on the geographical North and South poles. The geomagnetic North Pole, based on the Earth's magnetic field, is something like 700 miles south of the geographic pole, roughly on the west coast of Greenland. In addition, the center of the magnetic field is somewhat displaced from the Earth's true center. For these reasons and a few others, we find that coordinates based on geomagnetic north and south poles must appear on this type of projection as curves, something like these overlaid lines. Since the Earth's magnetic field is not really symmetrical, the exact coordinates would be even more eccentric than these in some areas, but this pattern is a handy convention. Notice that the geomagnetic equator dips quite far south in the Atlantic. Now, for the Argus operation, we wanted two things: an inconspicuous firing area and a stable instrument platform for observation. These requirements could be met by the choice of the Azores for an observation base and the South Atlantic for a firing area. Working from the fixed Azores location as one end or conjugate point of a given set of magnetic field lines, the other end fell in an area a bit south of Gough Island, roughly as far south of the geomagnetic equator as the Azores are north of it. This southern conjugate point, then, more or less automatically became the firing point. During the time of the task force preparation and move to Point Lima, the other requirements for the operation were also being pushed. I mentioned earlier that artificial Earth satellites were scheduled to do a major portion of the work in locating any electron shell we might succeed in establishing. In this plan, Army's Ballistic Missile Agency was to launch two satellites, Explorer 4 and Explorer 5. Explorer 4's telemetering instrumentation of two scintillation counters and two Geiger counters was designed to count and report particles in 4 different energy ranges, with thresholds for electron energies at about 30 keV, 600 keV, 2.5 MeV, and 5 MeV. The backup satellite, Explorer 5, would have contributed valuable supplementary data, but it failed to go into orbit when the launching attempt was made. On July 26th, however, Explorer 4 was launched from Cape Canaveral and went into orbit successfully. It became the workhorse of the whole project from the standpoint of telling us what was happening. As a starter, it accumulated a great deal of valuable background data between the time of its launching and the first Argus shot a month later. As I mentioned earlier, a satellite reaching high enough latitudes will go through an electron shell 4 times on each pass around the world. If its location at given times can be accurately determined from good ephemeris data, then the time at which it telemeters a report that it is passing through a zone of high electron density will tell us accurately where that zone is. Explorer 4 had a diagonal orbit reaching to about 51 degrees north and south latitudes. For explanation purposes, we can think of this orbit as a more or less fixed and unchanging ellipse, with the world rotating once a day inside of it. It took the satellite something like 2 hours for each pass around the world. During the time of each trip, then, something like 2,000 miles of equator would rotate under the orbit. As the satellite comes around on its next pass, this part of the world will lie under the orbit. 2 hours later, this part. In this way, in time, the satellite would scan the area over the entire world, with the exception of the regions above and below its highest latitudes. Only a satellite with a roughly north and south orbit could have scanned those areas. To track and to read and record the telemeter data from the satellite, we had a net of microlock and Minitrack stations spotted at many places around the world, both in the United States and in foreign areas. Most of these were IGY stations set up for the Navy's Vanguard program, but easily adapted and extremely useful on this job. Others were designed from the start to work on the Army ballistic missile program and furnished most of our early, clear returns on the satellite's findings. Another satellite launching concept was tried by the Naval Ordnance Test Station in California. A 5-stage rocket some 16 feet long was the vehicle for this plan. The instrument package to be put into orbit had to be held below 3 pounds, but with this small size and weight, the rocket could be carried to altitude by an airplane and released in a sort of upward lob that would give it considerable vertical component. Then the motors would begin to fire to take it on up and over into a low orbit path. The fifth stage motor had a long delay, being timed to ignite after the rocket had gone halfway around the world, so that the rocket kick of the reversed fifth stage would be in the right direction to accelerate the instrument package into a higher and more stable orbit. 6 vehicles for this economical concept were assembled and tested, but various difficulties prevented the achievement of stable orbit by any of them at this stage of the concept development. Still another means of searching for and sampling the Argus electron shell was the Air Force Special Weapons Center program based on sounding rockets. Firing sites for this program were located at Patrick Air Force Base, Florida, Wallops Island, Virginia, and Ramey Air Force Base, Puerto Rico. These 5-stage rockets were designed to reach altitudes like 400 miles and were instrumented to count particles with energy thresholds ranging from roughly 0.2 MeV to 5 MeV and telemeter the findings to ground stations. Instrumentation for ground observation of Argus effects was the responsibility of the Air Force Cambridge Research Center. Up north, aboard ship and on the Azores, instrumentation was provided to measure visible auroral effects, their extent and duration, as well as the spectral character of the light emitted, the character of possible radar returns from the induced aurora, variations in the ionosphere caused by the trapped electrons, and perturbations of the Earth's magnetic field induced by the detonations. To widen the observational area, aircraft were assigned to operate out of Lodges Field in the Azores, equipped to measure optical phenomena and perturbations of the ionosphere. The USS Albemarle was also stationed in the vicinity of the Azores to provide a relatively stable but mobile observation platform, instrumented to look for conjugate point phenomena. It may appear that the instrumentation of the conjugate region was over-complex. However, it should be borne in mind that negative data, information that some given effect did not occur, could prove as valuable as positive data. With the task force on station at Point Lima, Explorer 4 in orbit, the sounding rockets and ground instrumentation ready, the time approached for the first firing. While the weather was uniformly raw and uncomfortably chilly, no severe freezing or icing was encountered at any time, even though the operation was not any great distance from the Antarctic ice pack. Weather forecasting was aided by occasional reception of South American or South African radio broadcasts. Beyond that, the task force was dependent on its own Weather Central findings. Winds were more or less uniformly in a range from 15 to 40 knots, usually around 25. One storm had gusts up to 65 knots. Tracking of the Raywin balloons gave us the ballistic wind, the composite wind vector made up of all the significant wind layers up to around 10,000 feet. This composite wind had to be cranked into the launching data of the missile to obtain a near vertical launch, necessary to reach the desired altitude. To track the X-17A rockets and to locate the burst points, MSQ-1A radar vans were placed aboard Tarawa and Neosho, which were to stand off 15 to 20 miles from the launch ship at each firing to secure a reasonably wide tracking angle. As it turned out, the MSQ-1As were not adequate for this type of missile, with its great range, high acceleration, and large dispersion. Unlimited range without manual recycling and ability to track up past 90 degrees without rotating the antenna would be mandatory for good performance. Also, stabilization for the antennas against pitch and roll should be devised for any future assignment in this category. The shipboard launch environment made it impractical to use the normal practice of firing exactly at some pre-selected instant. Instead, when the firing keys were closed, command was taken over by a stable element, which would not close the firing circuits until a preset combination of pitch and roll had been obtained. For this reason, it was never possible to determine ahead of time just how many seconds there would be between the manual firing command and the actual launch. About 3/4 of an hour before zero time, Tarawa launched photographic and observation aircraft to climb above the heavy cloud layer and watch for burst phenomena. With the aircraft on station and arming procedures begun, all hands were sent under shelter for protection against vehicle malfunction or falling stages. Minutes later, the firing keys are closed and the stable element takes over. Approximately 2:30 a.m., 27 August 1958. This was the first known firing of a rocket missile with a nuclear warhead from a naval vessel. It was the first known instance of any type of nuclear weapon being fired from any vessel by any means. With the rocket launched, Norton Sound broadcast "Buzzer away." Tarawa, at 0 plus 60 seconds, notified the aircraft 6 minutes to flashlight, and then counted down the minutes while the aircraft turned on their cameras at scheduled times. Some 7 minutes after the launch, shipboard watchers saw a horizon-wide flash brighten the cloud layer. One aircraft observer who was above the clouds saw a yellow-white flash wider than the full moon, a wide, pale reddish ring, and then greenish auroral streamers running magnetic north and south and persisting for some minutes. That was shot one. Our radar records were inadequate to position the burst any more accurately. It was assumed that the trajectory had been too low and that the third stage had probably not fired. It seemed questionable whether the low burst height would fulfill Argus effect requirements unless convection raised enough fission products to heights where their beta decay electrons could be satisfactorily trapped. Our best guess as to where the conjugate point of the burst would be found was somewhere in this area below the Azores group. If the Argus effect electron shell defined by these conjugate points were set up around the world, we hope to locate the northern edge of the shell running parallel to the geomagnetic latitude lines belonging to this region, though not necessarily on top of this particular sample line. After the shot, there were some inconclusive reports of an aurora sighting and of a radar return in the cloudy Azores area, and that was all from there. Returns from the high-altitude sounding rockets at Wallops, Patrick, and Ramey were doubtful or negative at that time. However, a quick-look readout from the Army microlock station at Huntsville, Alabama, indicated a band of increased particle count some 200 miles thick and 2 to 5 times background in areas high above Haiti, Mexico, and Baja California. By extending the magnetic field lines running through these spots down to where they would intersect the Earth's surface, we derived what we called ground intercept points. It was reassuring that these points lay along a line close to and roughly paralleling the geomagnetic latitude lines where we expected to find them. It indicated that we had indeed trapped electrons in the Earth's magnetic field. However, because of the negative results from other projects and the low altitude of the burst, Task Group 88.6 headquarters concluded that a second shot was required. In order to put the conjugate point farther north so that observers would be under the expected phenomena and be able to get better measurements, it was recommended that the launch be made from a point farther south than before. Task Force 88 was standing by in the South Atlantic during these deliberations. Fuel to last out any reasonable operational period was no problem because of the presence with the force of the oilers Neosho and Salamone. When the word for shot number 2 came down, the ships moved to a point approximately 200 miles farther south. After a wait of 1 day on account of high winds, the second X-17A was launched at roughly 3 a.m. of 30 August, the third day after shot 1. The burst was a very bright flash to those on board ship, even through an obscuring cloud layer. Observers in Tarawa's aircraft were above the clouds and reported a bright flash and a brilliant yellow area expanding to perhaps 15 degrees across, deformed within minutes to a yellowish streak running magnetic north and south across 50 or 60 degrees of sky. The radar returns on the missile flight were again incomplete. There was heavy clouding at the northern conjugate point. and neither Albemarle nor observers at ground stations saw any significant visual or radar returns. Then Explorer 4 data began to arrive from Huntsville, reporting that a high-energy electron shell had again been established. Plotting the ground intercepts to locate the northern edge of the new shell, it appeared that the line fell almost on top of the Shot 1 line. Preliminary reports from the station at Torrejon, Spain, tended to confirm this puzzling news. The situation was rather upsetting. Since Shot 2 had been fired almost 600 miles farther south than Shot 1, its conjugate point should have been almost the same distance further north than number 1's. But they were almost together. There was a hold on the operation for another 5 days while Task Group 88.6 took a closer look at the information. The uncertainties of Shot 2 made planning for a decisive Shot 3 quite difficult. It appeared possible that the satellite was still reporting the presence of Shot 1 material, and that Shot 2 material had somehow been overlooked on the tapes. Even so, it was difficult to know where to look. At this point, Albemarle was sent south of the Azores to see if any effects could be located there. Nothing significant was found. It was tentatively decided to leave Albemarle there, send the Air Force C-97 to look northward, and fire number 3 from a point still farther south than number 2. A complicating factor during this time was that one of the sounding rockets fired from Wallops Island right after Shot number 2 had reported a zone of strong activity well to the north of Shot 1's shell. This report led to a closer scrutiny of the satellite reports. It was finally determined that an ephemeris error had accumulated since Shot 1 to a total of almost 2 minutes, putting our determination of the satellite's position off by that much. Correcting for this, moved the ground intercepts northward by some 500 miles, and we were in business again. This was more like what had been expected. I would like to point out again, however, that this sample geomagnetic latitude line is only a first approximation, and our results should not be expected to parallel it exactly. The launch point previously selected for Shot 3 was kept, and Albemarle was moved up to look for conjugate point effects to the northwest of the Azores. Shot 3 was fired roughly 2 hours before midnight, 6 September. There were no clouds, and the flash of the explosion 7 minutes later was clearly visible to observers in the task force, as well as to those in the observation aircraft. The flash was extremely brilliant. Then, in a second or so, a bright yellowish band streaked some 40 degrees across the sky toward magnetic south. Watchers on the ships reported a brilliant greenish aurora around the southern end of the streak. This time, the sky was also clear up north, and Albemarle reported seeing a mild auroral glow about 6 degrees wide, bearing approximately 280 degrees true. Furthermore, the ship's radar found a 30 megacycle echo on the same line and lasting half an hour, some 400 miles away. These items locate the true conjugate point of the last shot only roughly, since they were quite possibly not caused by electrons, but by heavy, low-energy positive particles which would migrate west of the true conjugate point. However, the effects do define the conjugate point latitude line pretty well. The satellite, Explorer 4, again found high-energy electron zones in the exosphere, this time where they were anticipated. The ground intercepts defined a geomagnetic latitude line that fell very close to the one from Shot 2, and again conformed within reason with the contours originally calculated for this area. At this point, the active phases of the operation were about over. The task force prepared to return to port, and the head-scratching over miles of data tapes got underway. For one thing, the best fit to our shipboard firing and radar data has indicated that the third stages of both Shot 1 and Shot 2 failed to fire. This was probably due to environmental conditions under which the X-17A had never previously operated, and which there was not time to test for before the operation. When all the results were pulled together, they proved qualitatively the existence of the Argus effect. Establishment of electron shells derived from beta decay of fission products in the exosphere has been demonstrated. After each detonation, all detector channels of the satellite reported concentrations of high-energy electrons in areas where theory said such concentrations should exist. There's apparently only a relatively slight diffusion of the shuttling electrons in directions that would carry them to higher or lower layers. However, the average half-life of the electrons was only something like 24 hours. This figure, of course, applies only at the altitudes at which the satellite sampled the shells. Lower down, collisions with air molecules would obviously shorten the mean lifetimes. Those electrons with high mirror points probably have much longer lifetimes. Just how long can only be reliably determined by data from a satellite with a much higher apogee, of at least 1 Earth radius, and preferably in a transpolar orbit for maximum benefit to this and other important research. I should mention here that the Argus experiment not only gave us data on urgent military considerations, but also produced a great mass of geophysical data, pure scientific material of great value. This pretty well covers the superficial technical aspects of the project. Admiral Parker will complete his report.
A successful operation was conducted in which nuclear detonations were delivered from the desired locations to the designed altitude. The 3 shots, although not all ideally successful, provide vastly more information than would a single successful shot. Good definitive data were obtained on Explorer 4 instrumentation for all 3 shots as a function of electron energy, as a function of time, and at various locations around the Earth. From these data, many parameters in the Argus theory can be evaluated. The satellite portion of the test was highly successful, even though we lost Explorer 5. In addition, it appears that the sounding rockets obtained data at locations and times which will supplement the satellite data. The stations of the ground instrumentation program in general obtained the data for which they were designed, although the locations of the conjugates for the 3 shots were not as well defined as we had hoped for. It appears that extensive theoretical study is required to determine the electron trapping and spreading mechanism. It is not clear just why the lower altitude shots were able to produce significant Argus effects. However, from the overall results, the military implications and applications can be evaluated. Argus was a large and complex project, a worldwide laboratory experiment. It was undoubtedly the largest scale single geophysical experiment ever programmed. Yet it was carried out under the considerable handicap of a top-secret restricted data classification. This was imposed mainly by political necessities and maintained so successfully that very few of the actual operational personnel ever knew the relation of their activities to the whole Argus experiment. From the angle of the pressure of time, we can point out with pride that Argus was examined, approved as a project, assigned, prepared for, and executed in only 5 months. This in itself was a substantial achievement by all hands. This concludes my report on the Argus experiment.